and we'll start with week 9 notes, and I'd like to also at the end of the notes today show you some reinforcing plans and schedules, because that's the first thing we've got to draw. And I'll give you a wee bit of a lead into how to start and what to draw, and you've still got to do the maths and work it all out. And I'll let the class student know how far they can, take it, and how much they can show you of the assignment, and otherwise they can do the example from last week again if you didn't understand some of that. And then in our class today, you'll see there it says steelwork, no answer. We're going to do a girder in our lab class. A girder is the sort of thing that you might expect in a mechanical garage. I don't know how many of you have seen the Fast and Furious. There's been about 9 of those movies, and they're always got a big ball and chain thing that they've got going across the garage, which they haul the engine up, put another engine in, whatever they do with the cars. And it's quite common for most garages to have a beam that's been reinforced quite a bit, going across the roof line of the garage. So we're going to do one of those. When I say we're going to do it, we're going to schedule it, which means in the end we'll put the numbers in and we'll work out the quantities. The quantities are something you're going to have to do for an assignment with the steel structure that's called a portal frame, and also the steel plates, and there's little angles that are welded to the top for the purlin to go on. I'll go back to week 9 and I'll show you what I'm talking about. Sorry, week 8. Hollow, and I'll get to that later on in the notes. This is a flat plate, and this up here is the angle I was talking about. I'm going on in a bit there, with the L shape, I suppose. So the angle would be welded onto here at this stage. I can't remember what the notes say. I believe it's welded on, and this would be welded on down the bottom down here. There'd be 4 holes in this plate, and it would be dynabolted into the concrete. There would be some lag screws going through here, which are a bit like bolts, but they screw into a smaller hole drilled into the timber. So, in scheduling the steel work here, which is the little wee red things and the green parts, you're going to have to produce a table. It's already on my example, and I'll show you how to do that in the lab class with a small example of the girder. The other thing about the girder is it's also in the test with different members. So if you understand the logic behind it, it should be the easiest test you've done for a while. Now, the degrees, and there's only about 8 or 9 of them, they wangled 3 half marks out of me yesterday. So we'll see what you guys can do at 8:30 in the morning in your lecture. So try and keep awake. There's some opportunities. It may not seem like much, but if you have a look at the marking schedule, the students that, some of their CAD was not quite right, got a half a mark taken off, and the ones that got the half mark in the class, it just balanced it out. They didn't have to worry about that, they got their raw mark. So 5% is, 5 marks is, half a mark out of 20 is what? 2.5%. So you'll notice I didn't really give anyone any more than half a mark off unless they had really bad things happening, multiple CAD issues going on, or they hadn't fixed up a whole lot of stuff in assignment 1 and just took it through to assignment 2. Back to the notes. should be able to see the notes. Like I said, I've made them available week 9. So as we go through, usual story, I'll point out anything that you need to go back to look at for the test. Now, some of you would have realised that the test isn't as easy as it might have looked, because open book doesn't really mean, oh, here's all the answers, and you weren't given like all day to do it, or in a lab where you're all shouting the answers to each other, which I tried one year. That was really clever. I just let the students do it on their own, and of course the top student did it all, and then she started yelling out all the answers to everyone else. No, you've got to read through the notes 2-3 times, and then when it comes to the test, some of those things you'll get right, and others you'll go, oh, I know where to go for that. Flick, 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 oh, there's the answer. Right? But if you haven't read through your notes 2 or 3 times, it's like, oh, where's that in the notes? And you've wasted 4 or 5 minutes looking for the answer, which might not even be there. Right? So I'll go through and tell you those things. I'll tell you what is needed, what might be useful for the assignment, and we'll cover the notes section. Now, a lot of this is repeat from the material, not all of it, but there's some really good notes for your assignment in here that you can almost copy straight away. I'll talk about structural steel in industry as well. A really good friend of mine works as a manager at Fletcher Steel, so it's quite interesting. Socially, we start talking about, you know, normal boy stuff, and within minutes we're talking about steel. Okay, so I do have a bit of a background, shall we speak, in reinforce in the concrete side of things, but I've only worked with steel for 3 or 4 or 5 years in a consultancy office, and I'm going through the concrete stuff now. We'll get there. But nevertheless, I have done a number of buildings, and I have done a number of what we call pipe supports for geothermal in different countries as well. So why do we use steel? I saw a domestic build the other day over in Green Bay, and it was all steel, and I thought, wow, that's going to cost a bit of money. But I drove past a few weeks later, and they already had the roof on and the sidewalls attached. And I suppose if I drove past in another couple of weeks, they'll just about be finished. The advantages in steel is that you never get walls that look like this, because the chippies have not quite stood them up right, or it wasn't produced right. Steel doesn't have that same shrink and expansion thing going on as what timber does. Timber dries out, shrinks. Timber gets too much water in it, it swells. It has disadvantages as well, but I think the main one is the assembly. You can put these steel buildings up pretty quickly. The second one is you don't have to worry about moisture content. With domestic wooden builds, they will not let you put the lining on unless they put their little, they poke their little prod in there, and it's got to be 15% or less moisture content. So that's a real advantage if you're lining your building. And as I said, they go up pretty quickly. I don't know, I've often picking up or dropped off people from the airport, friends and what have you, family, and you drive out there and there's just hundreds of factories being built out that way. You drive to pick them up, there's a slab on the ground, you come back a week or so later and drop them off and say goodbye, and you, is that the same building I just drove past? Oh, it's another you know, big factory just being built. So a lot of companies work to deadlines. They need things up in time for a shipment that's coming in, and steel tends to be the dominant one. Which leads us to this chart here, which is an example only of what you get from a steel company. Now, I haven't started to explain some of these members, but they are different shapes of steel, and I'll talk about them later. But let's take your ordinary beam. So there's a big column there, there's another one over here. And you're trying to size a beam to go across there. And you've made your building 13, 14 metres, say 13 metres long, and you've done your calculations for your structural member, and you've worked out the size of your beam. So you'll go to a chart that the steel companies provide, and you go, oh damn. You look up here, there's lots of 12 metre ones, but when you come all the way down, there's a lot of not so many 13 metre ones. So the logic would say either build your building 12 metres or 16 metres. And you say, well, why? We just chop a bit off the end. That's true, you can do that. But I don't know if you've ever held a beam before. They're very heavy, and that is what the price is. It's on prices. Imagine if that was gold, and you said, take a big chunk of gold off, just throw it away. Yeah, it's the same sort of thing with steel. Steel's worth quite a few bob in New Zealand anyway. Which leads back to why you schedule it. There's a cost of steel per kilogram, and you'll have a number at the end of your scheduling, and that'll give you a really good idea of what the cost is going to be. As an example, I built in Blockhouse Bay 2015, so going back a little bit now, we were talking with the designers, the architects, and Blockhouse Bay, if you don't know, faces the harbour, but it's very cold, faces south, so we needed some sun from the north, and we came up with this idea of a pitched roof with a small window coming through. We had to put steel columns and steel beams to frame the window out, to hold it up. It cost $35,000 for that window. I called it my $35,000 window. To give you an idea, a normal window that size, just put into a building, you'd be lucky to hit $1,000. It'd be more like about $500. So, yes, everything you do with steel is very expensive. So it's important as engineers that we get the right size so it doesn't fall down, but also get the right price for the client. Clients don't tend to like an extra 10 grand knocked onto their bill for no reason at all. So one of the ways you can do that is you can look at these charts and try and design your building around it. You go back to the client and say, oh, look, I know you wanted 13 metres, we can only do it 12. Can you make that work? Oh, but okay, yeah, I think I can make that work. Or, and you explain to them how much more it's going to be. Wastage. And that kind of goes for all the members that you might build. So if we were doing an angle like I showed you before, and the portal frame and everything else, you'd work out your portal frame lengths and make sure that they were available before you actually went ahead with putting the plans into council. So I've got this section here, but I'm going to skip that and I'm going to show you a little bit about what some of these things look like with this little picture. So you have round, hollow sections. You have your typical beam here. You've got this, which is an angle, and this, which is a channel. And when we're designing them in terms of working out where they're going to hold buildings up, we use these numbers here. T being the flange, and R, well, this here, big T, being a word. Little T, big T. Little T, big T, play school. Most of you are born too late to watch play school. I didn't watch it, I was born there. I was a father, I was a kid. We have universal beams, universal columns, rolled steel joists. Note the column is kind of rectangle, because they'll stand that up and it'll hold the beams up at, or basically the next story of the building up. So the forces are coming down on that in a different way than they are the beam. Beams are normally tall and skinny. Normally, you can get fatter ones, and you can use columns as beams. But generally speaking, they're the shapes we're talking about. Now the rolled steel channel, or TFC and PFC. Anyone tell me what TFC and PFC stands for? Half a minute. Although they didn't get this one. I'll give you a further clue. I called that a channel, right? The last letter stands for channel. And the second last letter stands for flanged.
Temporary and permanent.
Temporary, did you say?
Yeah, temporary and permanent.
No. And what was the other one?
As I said, T for temporary and P for permanent.
I didn't hear that last week.